In question 1, we are told that the discrete random variable x takes the values -1, 2, 3, 4, and 7 only. We are given the probability distribution here, and we need to find the expectation of x. It makes sense to start by drawing up a table with the possible values of x. So it's -1, 2, 3, 4, and 7, and the associated probabilities according to the function given here. So when x is -1, the probability turns out to be 9/k. For x is 2, it's 6/k. For 3, it's 5/k. Then it's 4/k. And then it's 1/k. We know that the sum of the probabilities should be 1. So 9/k plus 6/k plus 5/k plus 4/k plus 1/k must be equal to 1, and therefore we get that 25/k is equal to 1, which makes k 25. Now to find the expectation of x, we know that we multiply each value of x with its associated probability. So it's going to be -1 times 9/k plus 2 times 6/k plus 3 times 5/k plus 4 times 4/k plus 7 times 1/k, which gives an answer of 41/k. So this is 41/25, the expectation of x. In question 2, we're given a tree diagram with 3 options for a main course and then 2 options for a drink. In part A, we need to complete the tree diagram. We know the probabilities need to add up to 1 for each set of branches, so this should add up to 1. So 0.4 plus 0.35 is 0.75, which makes the third probability 0.25. And then for this branch here, we've got P, the probability of water. So 1 minus P for juice, then 1 minus Q for juice, and then 0.60 for juice in the final branch. In part B, we need to find an expression in terms of P and Q for the probability that someone chooses water to drink. And we can actually follow the tree diagram to see that in order to end up with water as a drink, it could be meat and water, fish and water, or vegetarian and water. These are the 3 different combinations that lead to water. So we can say that for part B, the probability of water will be 0.40 times P. So we multiply the probabilities of the branches through which we travel, plus 0.35 Q, plus 0.25 times 0.4, which simplifies to 0.4 P, plus 0.35 Q, plus 0.1. In part C, we are told that the events choosing a vegetarian main course and choosing water to drink are independent, and we need to obtain a linear equation in terms of P and Q. Now, if 2 events are independent, it means that the probability of both happening is simply the product of the individual probabilities. So the probability of vegetarian and water is simply the probability of vegetarian times the probability of water. So we start by writing out this. It's the definition of independence. Then we follow the tree diagram. The probability of vegetarian and water is 0.25 times 0.40. The probability of vegetarian is 0.25. And the probability of water is 0.4 P plus 0.35 Q plus 0.1. This is what we obtain in part B above. Now the 0.25 cancels out, and I'm left with 0.4 is 0.4 P plus 0.35 Q plus 0.1, which leads to 0.3 is 0.4 P plus 0.35 Q. In D, we are told that the student who has chosen juice to drink is selected at random, and the probability that they chose fish for their main course is 7/30. we need to find the value of P and the value of Q. So we know for sure that they chose juice, so we are here, here, or here. And then the probability that they chose fish is 7/30, so it's this one here. So we know that we will be dividing the fish times juice over the meat juice, fish juice, and vegetarian juice probabilities, because this is an example of conditional probability. So in part D, we will simply say that 0.35 times 1 minus Q, this is the probability of choosing fish and juice, over the probability of picking juice, which is simply 1 minus the probability of choosing water, which was found to be 0.4 P plus 0.35 Q plus 0.1. All of this is equal to 7/30. We have also established that 0.4 P plus 0.35 Q from above is 0.3. So this is 0.3 here. And therefore we get that 0.35 times 1 minus Q over 1 minus 0.3 plus 0.1 is equal to 7/30. So 0.35 times 1 minus Q over 0.6 is 7/30. Now I can cross multiply to get that 0.35 times 1 minus Q is equal to 0.14, and therefore 1 minus Q is 0.4, which makes Q 0.6. Now that we know Q, we can go back to the equation here and say 0.3 is 0.4 P plus 0.35 Q. So 0.3 is 0.4 P plus 0.21. So 0.09 is 0.4 P, which makes P 9/40. In E, we are told that the canteen manager claims that students who choose water are most likely to choose a fish for main course, and we need to state showing the working whether this claim is correct. So we know for sure it is given that they choose water, so we are here, here, or here, and we are looking at the probability they choose fish. That's what we're looking for. So in other words, it's the probability someone chooses a fish given that they chose water. So this will be the probability of fish and water, which is 0.35 times Q, over the probability of water, which we found to be 0.4 P plus 0.35 Q plus 0.1. Well, Q is 0.6. P is 9/40. So I'm replacing the values I found for P and Q. And this is giving an answer of 0.525, which is greater than 0.5. So the manager was claiming that these students are most likely to choose a fish main course. And since the probability we found is greater than 0.5, we can conclude that the manager's claim is correct. In question 3, we've got the distance achieved in a long jump competition following a normal distribution with a mean of 3.8 and a standard deviation of 0.9. And we are told that those that achieve a distance of at least 4.3 meters will be receiving a medal. And we need to find the proportion of students who receive medals. So we could start by defining our random variable x to be the distance, and we know that this random variable follows a normal distribution with a mean of 3.8 and a variance of 0.9 squared. And so we're looking for the probability of x greater than 4.3. We'll standardize by deducting the mean and dividing by the standard deviation. So it's 4.3 minus 3.8 over 0.9. This is the probability of z greater than 0.56. Now I'm rounding the Z value to 2 decimal places because that's the accuracy to which the normal table works at. Now I need to make that into 1 minus the probability of Z less than 0.56, which turns out to be 1 minus 0.7123, which is 0.2877. In B, the school wishes to give a certificate of achievement or a medal to the 80% of students who achieve a distance of at least d meters, and we need to find the value of d. In other words, we need to solve the probability of x greater than d being 0.8. So we start again by standardizing. So z greater than d minus 3.8 over 0.9. This is equal to 0.8. We know that we will be using the small table of probabilities, which gives more accuracy. So I will make two changes. Instead of d minus 3.8, I will be doing 3.8 minus d over 0.9. And the 0.8 becomes 1 minus 0.8, which is 0.2. From the table of values, we get that 3.8 minus d over 0.9 is equal to 0.8416, and therefore 3.8 minus d is equal to 0.75744, which makes d 3.04 to 3 significant figures. In part C, we are told that of those who received medals, the third who jumped the furthest will receive gold medals, and we need to find the shortest distance, g meters, that must be achieved to receive a gold medal. Now, this is an example of conditional probability with a normal distribution. It makes sense to draw a bell-shaped curve and try to illustrate all the given information there. So we start off with the bell-shaped curve centered at 3.8. We know that the probability of exceeding 4.3 is equal to 0.2877. This is the proportion of people that are getting a medal altogether. And we need to find that value g such that the probability that we are above this is a third of 0.2877, which works out to be 0.0959. So given that we have exceeded the 4.3, so given that we are here, the probability we are more than g and therefore we'll be getting a gold medal will be 0.0959. So the probability of x being greater than g is 0.0959, which means that the probability of x less than g is 1 minus 0.0959, which is equal to 0.9041. I will now standardize the probability of z less than g minus 3.8 over 0.9 is equal to 0.9041, and this means that g minus 3.8 over 0.9 is equal to 1.31. So g minus 3.8 is equal to 1.179, which makes g equal to 4.98 meters. In part D, we have a journalist who is interviewing a randomly selected group of 3 medal winners, and we want to find the exact probability of at least one gold medal in this group of 3 people. So we are looking in the subset of people who have obtained the medal, and we're wondering what's the probability of having at least one gold medal in this group. So we know that among medal winners, a third of them are gold medal winners, so the probability of getting a gold is a third. So the probability of at least one gold is simply 1 minus the probability of no gold winners. And we know that if the probability of getting a gold is a third, then the probability of not a gold is 2/3, and we need to raise that to the power of 3 because I want all 3 members of this group not to be gold winners, and this gives an answer of 19/27. In question 4, for the group of students that took some tests, we've got the analysis conducted by the teacher, and we know that for these average marks, the lower quartile was 24, the median is 30, the interquartile range is 10. We are being given the 3 lowest marks and the 3 highest marks here, and we need to determine any outliers based on this rule here. In order to do that, I will start by finding the upper quartile. We know that the upper quartile Q3 is simply the lower quartile Q1 plus the interquartile range. So that's going to be 24 plus 10, which gives an answer of 34. Now, if we do the lower quartile minus 1.5 times the interquartile range, we get a value of 9. And if we do the upper quartile plus 1.5 times the interquartile range, we get an answer of 49. If we compare these limits against the lowest and highest average marks, we can see that 8, 52.5, and 56 are the only outliers. In part B, we need to draw a box plot for this data. I will draw the box plot here for you, and I will actually present 2 different box plots that you could have drawn, both of which are acceptable by the examiner. So in the first box plot, I have drawn the lower quartile, the median, and the upper quartile, and we have identified with a cross the 2 outliers on the right and the outlier on the left, and the whiskers go up to the last observations that are not an outlier. So we know that 10 was an observed mark, and this was the last value that is not an outlier. And on the right hand side, we know that 45 was observed, and it's actually the last mark not to be considered an outlier. An alternative, which is accepted because we've got outliers on either side of the box plot, is extending the whiskers up to the theoretical limits beyond which we'll find outliers. So in this second approach, which is acceptable, we go up to 9 on the left and up to 49 on the right, which are actually the theoretical limits we have calculated in part A while ago. In part C, we need to use the quartiles to describe the skewness. Now Q3 minus Q2 is equal to 34 minus 30, which is equal to 4, and Q2 minus Q1 is equal to 30 minus 24, which is equal to 6, and therefore we can say that Q3 minus Q2 is less than Q2 minus Q1, which means that we've got negative skew. We are then told that 2 more students also took the tests. Their average marks were both less than 45, and they are added to the data, and the box plot is redrawn. The median and the upper quartile are the same, but the lower quartile is now 26, and we need to redraw the box plot based on the 2 new marks which are added to the data. So I need to go through the process of recalculating the interquartile range and the limits for outliers. So we will start by doing that. We have that the interquartile range is 34 minus 26, which is equal to 8. Now 34 plus 1.5 times 8 is 46. This is the upper limit for outliers. And 26 minus 1.5 times 8 is 14, which means that we now have 2 outliers on the left, the 8 and the 10. And on the right, we still have the 52.5 and the 56 being outliers. So a total of 4 outliers. And again, there are two different box plots which are acceptable by the examiner, and we will once more draw both of these for you to look at. So once more, in the first case, we stop at the last observation that was not considered an outlier, so 45 on the right and 15.5 on the left. We still have with crosses the two outliers on the left and the two outliers on the right. And then the alternative is to go up to the theoretical limit, which is the 14 we calculated before on the left, and the 46 that we calculated on the right. In part E, we need to give ranges of values within which each of these students' average marks must lie. So I will start by observing that since the median remained unchanged, then one must be below 30 and the other must be above 30. We can then say that since Q1 increased, that means that one observation is between 26 and 30. So if the lower quartile has increased, then that means that the observation that is below the median is greater than Q1. And the final thing we can say is that since Q3 remained unchanged, this means that the other observation is between 34 and 45 in here. So the higher of the two observations is between 34 and 35. In question 5, it's a large company that's renting shops in different parts of the country. Now we have data for 10 shops and we are measuring the floor area X in 10 square meters and the annual rent Y in thousands of dollars. Now we have the regression line here and we are asked to use it to estimate the annual rent in dollars for a shop with a floor of an area of 800 square meters. Now we need to convert, first of all, the area of 800 square meters into a value for X. So this means that X is 80 since we measure the X in 10 square meters. And then we substitute Y is 6.066 plus 0.136 times 80. This gives a value of 16.946 and therefore it's $16,946. In B, we need to find the value of SYY and SXX. So I will start with the definition of SYY. It is sigma y squared minus sigma y all squared over n. In our case, it's going to be 3,434 minus 183 squared over 10, which gives an answer of 85.1. And similarly for SXX, it's going to be sigma x squared minus sigma x all squared over n, which is equal to 84,818 minus 900 squared over 10, and this gives an answer of 3,818. For part C, we need to find the product moment correlation coefficient between y and x, and in order to do that, we need the value of SXY. I will be using the regression line here, and the fact that the gradient, the 0.136, is SXY over SXX. So let me start by writing this down. 0.136 is SXY over SXX. We have found the value for SXX to be 3,818. So if I cross multiply, I get 0.136 times 3818 to give me SXY. This turns out to be 519.248. And therefore now I can proceed with the calculation of the product moment correlation coefficient. It is SXY over the square root of SXX SYY, and this gives 519.248 over the square root of 3818 times 85.1, which is 0.9109. In part D, we've got an 11th shop added to the sample. It has a floor area of 900 square meters and an annual rent of $15,000. We need to use a formula here for SXY to show that the value of SXY for the 11 shops will be the same as the one for the original 10 shops. So for this 11th shop with a floor area of 900 square meters, we can see that its X will be 90 and its Y will be 15. Now, the original mean was 90. And we have this 11th shop having exactly the same area as the original mean, and therefore the new mean will stay at 90. So this means that the contribution to SXY will be 0, since we'll have X minus X bar being 90 minus 90, which is simply 0. This means that SXY will stay the same. In E, we need to find the new equation of the regression line of y on x for the 11 shops now. So we start by noting that SXY remains at 519.248. And then we say that SXX, which is simply sum of x minus x bar squared, will remain at 3818, because again the contribution to this quantity is 0 because the new observation was exactly at the mean. Now we'll find the new mean of the y's. So y bar is simply the sum of the y's over n. We had the sum of the 10 first values to be 183 and the 11th value was a 15. So 183 plus 15 over 11 turns out to be 18, that's the new mean. We are looking for the equation of the regression line, so y is a plus bx. So we can say that b is sxy over sxx, which is 519.248 over 3818, so it remains the same. It remains at 0.136. And then for a, it's gonna be y bar minus bx bar. So it's going to be 18 minus 0.136 times the new mean, which is 90 as before. And therefore, this gives an answer of 5.76, leading to the new equation of the regression line being 5.76 plus 0.136x. In part F, we are told that the company is considering renting out a larger shop with an area of 3,000 square meters. And we need to comment on the suitability of the regression line used to estimate the annual rent for this shop. Now, if we look at the sum of the 10 values, it's 900, and this shop alone has a value for x, which is 300. So this certainly means that this shop has an atypical large area. So it's a lot larger than the average shop used when we were calculating the equation of the regression line. And therefore, we are extrapolating, we are predicting or estimating beyond the range of observed data, and therefore the regression line will not be suitable for this estimation. So we say that 3,000 square meters is a lot larger than the average shop in the sample. The regression line will not be suitable as it involves extrapolation. It is important to note here that we need to explicitly compare and refer to the numbers in order to get the 1 mark here to say that 3,000 square meters is greater than 900 square meters, which was the average shop size used when calculating the regression line. In question 6, we've got this random variable a taking values 1, 4, 5, and 7, and we need to show that the expectation of a is 3.5. So as always, the expectation is given by multiplying together the values of the random variable with the associated probability. So the expectation of a will be 1 times 0.40 plus 4 times 0.20 plus 5 times 0.25 plus 7 times 0.15, and this is giving an answer of 3.5 as required. In part B, we need to find the variance of A. So to do that, I will start by finding the expectation of A squared. So I take the value squared times the associated probability. So it's going to be 1 squared times 0.40 plus 4 squared times 0.20 plus 5 squared times 0.25 plus 7 squared times 0.15, which gives an answer of 17.2. And now the variance of A is simply the expectation of A squared minus the square of the expectation. So this would be 17.2 minus 3.5 squared, which gives an answer of 4.95. In part C, we are being told that the random variable capital B represents the score on a four-sided die. It can take values 1, 3, 4, and k, with all the probabilities being the same. Write down the name of the probability distribution of B. Well, because all the probabilities are the same, it's a uniform distribution, and because it's a discrete random variable, the answer is discrete uniform distribution. The key word here to get the mark: uniform. In D, we are told that the expectation of B and the expectation of A are the same, so state, giving a reason, the value of K. Now, the quick method is just to say by symmetry. And why does symmetry work here? Well, if the mean of B is 3.5, which is halfway between 3 and 4, that means that 1 and K, their midpoint should also be 3.5, and it's easy to see that K must be 6 here, so that 1 plus 6 over 2 is 3.5. The alternative is just to say that to find the expectation of B, I would be doing 1 times 0.25 plus 3 times 0.25 and so on. So it's going to be a quarter times the sum of the values. So we could do that just to confirm that it will work out to be 6, the value of K. So 1 plus 3 plus 4 plus K over 4 is equal to 3.5. And therefore 8 plus K is equal to 14. So K is 6. Or as we said, you could have alternatively said simply by symmetry. And that would be acceptable by the examiner. We are then told that the random variable x follows normal with mean mu and standard deviation sigma. And we've got Sam and Tim who are playing a game. Now the value of A will be their mu and the value of B will be their sigma. And the person with the larger value for probability of x being greater than 3.5 will turn out to be the winner. We know that Sam obtained the values of A is 4 and B is 3, and Tim obtained B is 4, and we need to find the probability that Tim wins. So to do that, we'll start by looking at what Sam has done up to now. So we know that Sam has obtained the values of A is 4 and B is 3. So his random variable x follows normal with mean 4 and standard deviation 3. So the probability of x being greater than 3.5 will be the probability of z greater than 3.5 minus 4 over 3, which is simply the probability of z being greater than minus 1 over 6. I'm not interested in the probability, I'm interested in how can Tim get a higher probability. Now for Tim, we know that he has obtained B to be 4, and therefore his random variable x follows normal with mean A and standard deviation 4. The probability of x being greater than 3.5 is the probability of z greater than 3.5 minus A over 4, and we want this to be a greater value than what Sam obtained. So I will actually put this on a bell-shaped curve to see exactly what's happening. So this is my bell-shaped curve. We're talking about the z normal random variable, so it's centered at 0. We have already established that Sam's probability is here greater than minus 1 over 6. And we want the probability that Tim will win. Well, Tim will win if and only if they get a value here for 3.5 minus A over 4, which is to the left of minus 1 over 6. So this should be the 3.5 minus A over 4, because in that case the probability will exceed the Sam's probability, and therefore Tim will be the winner. So in other words, we need 3.5 minus a over 4 to be less than minus 1 over 6. I can cross multiply to get 21 minus 6a less than negative 4. So 25 is less than 6a, which leads to 4.17 being less than a. Well, if we go back to the table of values for the random variable a, we see that we are greater than 4.17 if we get a value of 5 or 7. So it's going to be 0.25 plus 0.15. So Tim will win if he gets values for a which are 5 or 7. So that's 0.25 plus 0.15, which gives an answer of 0.4. In F, we are asked to find the largest value of probability x greater than 3.5 achievable in this game. So I will say that we are looking at the probability of x greater than 3.5, which is the probability of z greater than 3.5 minus mu over sigma. I will draw again a bell-shaped curve just to see what's happening. So there it is, it's centered at 0 once more. 3.5 minus mu over sigma is here, and I would like to make this region here as large as possible. So we want to make 3.5 minus mu over sigma as negative as possible. For this to happen, we need mu to be as large as possible and sigma to be as small as possible, and this will happen if mu is 7 and sigma is 1. So setting mu is 7 and sigma is 1 will make the probability of x greater than 3.5 be the probability of z greater than 3.5 minus 7 over 1, which is the probability of z greater than minus 3.5, which is simply the probability of z less than 3.5, which turns out to be 0.9998. In G, we need to find the probability of achieving this value. So the probability that A attains a value of 7 and B a value of 1. So the probability of A is 7 and B is 1 will be 0.15 times 0.25, which works out to be 0.0375.